Hello, friends. Welcome back. Some nights when the sky clears and the world grows quiet, you might look up and see it. A small red dot, steady and ancient watching from the dark. Mars. The planet of fire, they called it, in China. The rust-colored wanderer. For thousands of years, we've told stories about it, built myths around its glow. But recently, something changed. We stopped imagining. We started listening. In May of 2021, a small rover touched down on Martian soil. Its name was Zhurong, after an ancient Chinese god of fire and light. And what it found there buried beneath the dust wasn't what anyone expected. Not rocks, not craters. Something older. Something that whispers of oceans of waves, of a world that once looked nothing like the desert we see today. What was waiting there beneath the rust? What did the silence keep? Before we drift into that story, I want to say thank you for being here. If you find comfort in these quiet journeys through science and space, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's begin. Mars has always felt close, even when it's millions of miles away. On certain nights, you can see it without a telescope, just a faint red spark against the black. Ancient astronomers watched it wander across the heavens, moving differently than the stars. It didn't follow the rules. It looped. It paused. It seemed almost alive. The Egyptians called it Har-Jer, the Red One. The Romans named it after their god of war. In Sanskrit texts, it was Mangala, the auspicious one. But in Chinese, the name is simpler, more direct. Huaksang, fire star. For a long time, that's all Mars was to us. A light, a symbol, a question mark hanging in the sky. Then in the 20th century, we began sending machines to answer that question. Vikings in the 1970s, rovers in the 2000s. Orbiters circling cameras, clicking radars, pinging. And slowly, piece by piece, Mars started speaking back. Scientists suggest that billions of years ago, Mars wasn't the cold, dry wasteland we know today. Research shows it may have had rivers, lakes, perhaps even a vast ocean covering nearly a third of its surface. The evidence comes from valleys carved into rock minerals, formed only in the presence of water, and shorelines faint eroded, but still visible from orbit. It's as if the planet kept a diary written in dust and stone, waiting for someone to read it. China's space program had been watching Mars for years. They'd tried once before in 2011 with a small orbiter called Yinghuo-1. It never made it. The Russian rocket carrying it failed, and the mission disappeared into the Pacific. But they didn't stop. A decade later, they tried again. This time, they brought everything. An orbiter, a lander, a rover, all wrapped into one mission called Tianwen-1, which means Questions to Heaven. A fitting name for a journey into the unknown. On July 23, 2020, a Long March 5 rocket lifted off from Wenchang, an island launch site on the southern coast of China. Inside the payload, fairing sat the Tianwen-1 spacecraft, beginning a 202-day journey across 293 million miles of empty space. No corrections mid-flight, no second chances. Just mathematics, gravity, and faith that the numbers would hold. They did. On February 10, 2021, Tianwen-1 slipped into orbit around Mars, becoming China's first successful Mars orbiter. For 3 months, it circled cameras mapping the surface below, searching for the perfect landing site. And then, on May 14th, the lander separated. 9 minutes of atmospheric entry, parachutes deployed, retro rockets fired, and at 11:11 p.m. UTC, Zhurong touched down softly in a place called Utopia Planitia. Utopia Planitia. Even the name feels strange on the tongue. It's Latin for plain of paradise, though there's nothing about it that looks like paradise now. It's flat, barren, covered in rust-colored dust and scattered rocks. But it's also one of the largest impact basins in the entire solar system. a scar left by something unimaginably large that struck Mars billions of years ago. The crater is so wide, over 2,000 miles across, that standing in the middle, you wouldn't see the edges, just flatness stretching to every horizon. NASA's Viking 2 lander touched down here in 1976, sending back the first images of this desolate plain. But Viking couldn't dig. It couldn't see beneath the surface. Zhurong could. The rover carried ground-penetrating radar, a tool that sends radio waves deep into the soil and listens for what bounces back. Different materials reflect differently. Ice, rock, sand. Each has its own signature, its own voice in the static. Scientists chose Utopia Planitia for a reason. Orbital images had shown something unusual, a series of escarpment steep slopes that cut across the landscape in long parallel lines. From space, they looked almost like ancient shorelines, the kind that form when waves lap against a coast for millions of years. Some researchers believe that billions of years ago, this entire basin might have been filled with water. Not a lake, an ocean. One that covered nearly half the northern hemisphere of Mars. It was a bold hypothesis. Not everyone agreed. Some argued that the features were too eroded, too ambiguous, that Mars had been cold and dry for too long, that any ocean would have frozen solid or evaporated into space long before life could take hold. But the only way to know for sure was to go there, to touch the ground, to look beneath. On May 22nd, 2021, 1 week after landing, Zhurong rolled down a ramp and onto Martian soil. It was small, about the size of a golf cart, with 6 wheels and a flat solar panel stretched across its back like wings. It moved slowly, cautiously, maybe 200 meters on a good day. But it had time, or so the engineers thought. The rover was designed to last 90 sols, Martian days each about 24 hours and 40 minutes long. 90 days to explore, to photograph, to drill and scrape and measure. But Zhurong kept going. 100 sols, 200, 300. It trundled across the plain, following a route perpendicular to those ancient escarpments, using its radar to probe deeper and deeper into the ground. And that's when it found something. Not on the surface, below it. About 35 feet down, buried under layers of dust and volcanic rock, the radar detected structures that didn't match anything expected. Not random, not chaotic. Patterns, layers, slopes. Scientists analyzing the data noticed the angles first. Gentle inclines dipping at about 2 to 3 degrees, consistent across long distances. On Earth, that's the kind of slope you find on a beach, where sand gets washed up by waves and settles in thin, slanted sheets. The radar also measured the size of the particles in these buried layers. Sand-sized, not pebbles, not silt, sand. And the arrangement didn't look like windblown dunes, which tend to be steeper, sharper shaped by gusts and eddies. These layers were smooth, even, orderly. It seems as though water once moved here, gently, repeatedly, for a very long time. Dr. Michael Manga, a planetary scientist at the University of California, Berkeley studied the radar profiles with his colleagues. He told reporters that the structures didn't resemble impact craters, lava flows, or any volcanic feature they had seen before. The orientation was wrong, the texture was wrong, but they matched almost perfectly with coastal deposits on Earth, the kind you'd find along an ancient seabed, where sediment piles up grain by grain, shaped by tides and currents, and the slow, patient work of water. Research shows that these buried layers are roughly 10 meters below the present surface, preserved under a protective blanket of debris, dust from storms, ash from volcanoes, fragments from asteroid impacts. Without that covering, the delicate structure would have eroded away long ago, ground down by billions of years of wind and radiation. But here, tucked beneath the rust, it survived. A snapshot of a world that no longer exists, frozen in stone. Think about that for a moment. Beneath your feet, right now, beneath wherever you're listening to this, There are layers too. Sediment from rivers that dried up millennia ago. Fossils of creatures that lived before humans had language. Stone that remembers when forests stood where deserts stretch today. Earth keeps its history close pressed into the ground like pages in a book. Mars does the same. It's just that Mars's story is older, quieter, written in a language we are only beginning to read. The discovery didn't stop there. As Jurong continued its journey, the radar picked up more features. 16 distinct polygonal shapes buried even deeper, formed by something scientists call freeze-thaw cycles. When water seeps into soil and then freezes, it expands, cracking the ground into geometric patterns, hexagons, pentagons, irregular wedges. You can see the same thing in Earth's Arctic and permafrost regions where the ground locks and unlocks with the seasons. On Mars, these polygons suggest that water wasn't just flowing on the surface. It was cycling, freezing at night, melting during warmer periods, repeating over and over, carving its signature into the land. Some believe this means Mars once had something we've lost sight of in the present-day cold. Weather, real weather, clouds forming over an ocean, rain falling on distant highlands, snow settling on polar ice caps, then melting, flowing downhill, feeding rivers that poured into a vast northern sea. A water cycle, a climate, seasons that meant something. But here's what makes it haunting. The beach Jurong found, if that's what it is, dates back approximately 3.5 billion years. That's roughly the same time life was spreading across early Earth, thriving in tidal pools and shallow seas. Two planets separated by tens of millions of miles, both covered in water, both bathed in sunlight. One stayed wet, the other didn't. What happened? Where did the ocean go? Why does Earth have us and Mars has silence? We don't know yet. Maybe we never will. But every piece of data Jurong sent back is another clue, another fragment of a story that's been waiting 3.5 billion years to be told. And the rover kept going day after day, crossing ancient ground, its radar pinging into the depths, listening for whispers, until it couldn't anymore. In May of 2022, as Martian winter approached and dust storms began rolling across Utopia, Planitia Jurong went into hibernation. Solar panels dimmed, systems powered down. The engineers expected it to wake again in December, when sunlight returned and temperatures rose. But December came. Then January, February, silence. The rover never responded. Scientists suspect dust accumulated too thickly on the solar panels, blocking the light it needed to recharge. Jurong sleeps now, buried not in sand, but in the quiet that comes after the work is done. Yet even in sleep it speaks. The data it gathered is still being analyzed, still revealing details about that ancient shore. And the story it tells is just beginning to unfold. Because if Mars once had beaches, it had something more. Something vast and deep and full of possibility. It had an ocean. And we're about to drift into the memory of that world, to walk along shores that haven't seen a wave in billions of years, to imagine what it must have been like when Mars wasn't the red planet, when it was blue. Imagine standing on a beach you've never seen. The sand beneath your feet slopes gently toward water that isn't there anymore. Waves that stopped breaking 3.5 billion years ago. A shoreline that exists now only as a memory pressed into stone, waiting in the dark. That's what Jurong found, not on the surface where wind and time could erase it. Deeper, hidden, preserved like a photograph in a drawer no one's opened in eons. And the more scientists studied what the rover's radar revealed, the more impossible it became to deny. Mars once had beaches, real ones. The kind where sediment settles and water shapes the land grain by wave by patient wave. Ground-penetrating radar works by sending pulses of radio energy into the soil. These waves travel down, bounce off different materials, and return to the receiver with information. Rock reflects differently than ice. Sand has its own signature. Layers of sediment create patterns in the returning signal, like echoes in a canyon, each one telling a story about what lies beneath. Zhurong's radar could see as deep as 80 meters, peeling back the surface like turning pages in a very old book. What it saw starting about 10 meters down were layers. Thin bands of material tilted at shallow angles dipping between 2 and 3 degrees. That might not sound like much, but it's exactly the angle you'd expect from a coastal deposit. When waves carry sand toward shore, the grains don't drop straight down. They settle on a slope, building up gradually layer after layer, each one slightly offset from the last. Scientists call these structures clinoforms, and they're one of the most reliable indicators of ancient water activity. Dr. Benjamin Cardenas, a geoscientist at Penn State who studies Martian landscapes, has spent years analyzing similar features in satellite images and rover data. He explained that on Earth, you can walk along certain cliffs and see these same tilted layers exposed in cross-section, each band representing thousands of years of sediment deposition. Rivers carry material to the coast. Waves redistribute it. Storms reshape it. Over time, the beach grows, migrates, or disappears entirely. But the record stays locked in the rock. Research shows that the layers Zhurong detected aren't just tilted. They're also sorted by grain size. The radar measured particles roughly 0.1 to 2 millimeters in diameter. Sand. Not clay, which would be finer. Not gravel, which would be coarser. Sand. The kind you'd find on a shoreline where water has enough energy to move small particles, but not enough to carry heavy stones. Wind can create dunes from sand, but wind-blown dunes have different shapes, steeper slopes, and irregular patterns. These layers were too uniform, too orderly. They looked like something else entirely. Scientists suggest the formation process would have taken millions of years. Picture it slowly: an ocean lapping against the edge of a basin, sediment washing down from highlands in the south, carried by rivers that no longer flow. The material spreading across the shallow coastal shelf, settling where the current slows. Each storm adding a little more, each tide smoothing the surface. Seasons passing perhaps, with freeze-thaw cycles leaving their own marks. And then, over time, the water receding, the climate shifting, the beach drying out, and eventually being buried under dust and volcanic ash. That protective covering is why the structure survived. Without it, wind erosion would have stripped the layers away long ago. Mars has dust storms that can engulf the entire planet, winds that reach 60 miles per hour during peak season. For billions of years, those winds have been sculpting the surface, grinding rock into powder, erasing all but the most durable features. But beneath the ground, shielded from the relentless abrasion, delicate structures can persist. The beach was buried before it could be destroyed, entombed in stone, forgotten but not gone. The discovery raises questions, though. If these are beach deposits, where was the water line? How deep was the ocean? How far did it extend? To answer that, scientists turn to the slopes themselves. On Earth, beaches don't form randomly. They develop in response to wave action, which depends on wind-water depth and shoreline geometry. Shallow slopes, like the ones Zhurong found, typically occur in low-energy environments. Calm bays, protected coves, or the gradual margins of large, stable bodies of water. Not crashing surf, not violent tides. Something gentler, persistent. Dr. Hai Liu, a professor at Guangzhou University and a member of the Tianwen-1 science team, studied the orientation of these buried layers. They run parallel to what orbital data has long suggested might be an ancient shoreline, a feature called the Deuteronylus contact. This hypothetical boundary stretches for thousands of kilometers across Mars's northern plains, roughly following the edge of the Utopia Basin. If it truly marks the edge of an ancient ocean, then Zhurong landed right in the sweet spot, not in the deep water, not on the dry highlands, but in the transition zone, the shallows, the place where land and sea met. Some believe this wasn't the only beach on Mars. Ground-penetrating radar profiles from Zhurong's route show multiple sequences of these tilted layers stacked one above the other, separated by thinner bands of different material. That pattern is consistent with a coastline that shifted over time, advancing and retreating as water levels changed. Perhaps the ocean wasn't constant. Perhaps Mars experienced cycles, wetter periods when the water rose drier, stretches when it fell, each phase leaving its own signature, its own beach preserved in stone, like rings in a tree trunk. But here's where it gets stranger. The layers aren't just sand. The radar also detected pockets of what appear to be larger clasts, chunks of rock embedded within the finer sediment. On Earth, you find that kind of mixture in places where icebergs break apart and drop stones as they melt, or where powerful waves carry debris from farther inland. It suggests that the Martian coast wasn't static. Events happened there, perhaps floods from melting glaciers, perhaps impacts that sent tsunamis racing across the basin. The record is fragmentary, incomplete, but it hints at a coastline that wasn't just sitting quietly. It was active, dynamic. Scientists analyzing the thickness of the deposits estimate that the beach accumulated over a span of at least several 100,000 years, possibly much longer. That's not a puddle that evaporates after a summer rain. That's an ocean with staying power. An ocean that had time to shape the landscape, to carry sediment, to build shorelines that stretched across hundreds of miles. And it raises a question that keeps echoing through the data. If water was here for that long, stable enough to form beaches warm enough to stay liquid, what else might have been happening? On Earth, the earliest evidence of life dates back roughly 3.8 billion years. Tiny microbial fossils preserved in sedimentary rock. Stromatolites, layered structures built by colonies of bacteria in shallow water. Chemical signatures and ancient minerals suggesting metabolic activity. All of it found in coastal environments. Tidal zones, places where sunlight reaches the bottom, where nutrients wash in, from rivers where the boundary between water and air creates pockets of chemistry rich enough to support the first stirrings of biology. Mars, 3-5 billion years ago, had something similar, not identical. The sun was dimmer, then Mars farther from it than Earth. The atmosphere was different, the gravity weaker, the magnetic field already fading. But the basic ingredients were there. Liquid water, sediment-carrying minerals, sunlight filtering through whatever sky Mars had at the time, energy from volcanic heat or chemical reactions in the crust. If life ever started on Mars, the shallows of an ancient ocean would be one of the first places to look. Of course, we haven't found it yet. Zhurong's instruments weren't designed to detect biosignatures. The rover carried cameras, spectrometers, and radar, but no microscopes capable of seeing cells, no drills deep enough to reach truly ancient layers. The mission was about geology, not biology. But geology tells you where to search next. It narrows the possibilities. It says here, this spot, this is where conditions were right. Not everywhere, not always. But here for a while, maybe long enough. The irony is that the beach Zhurong discovered would have eroded away entirely if it had stayed exposed. Think about Earth's coasts. They change constantly. Storms reshape them. Rivers deposit new material. Sea levels rise and fall. In just a few thousand years, a coastline can look completely different. Over millions of years, the evidence vanishes unless something buries it. On Mars, that burial happened naturally. Volcanic eruptions from places like Elysium Mons, a shield volcano not far from Utopia. Planitia would have sent ash drifting across the basin. Dust storms, relentless and global, added layer upon layer. Asteroids striking the surface ejected debris that settled like snow. Slowly the beach disappeared under a blanket of time, but time also preserved it. Without liquid water to erode it further, without tectonic plates to fold and crush the rock, the beach stayed mostly intact, locked in place, waiting. Earth's tectonic activity destroys most of its ancient geological record. Subduction zones pull old seafloor into the mantle. Mountain building crumples rock beyond recognition. Mars, geologically quiet for billions of years, keeps its history closer to the surface. It's a museum of its own past. The thickness of the overlying material, about 10 meters, also tells scientists something about the rate of deposition. 10 meters of dust and debris accumulating over 3.5 billion years averages out to less than 3 micrometers per 1,000 years. That's incredibly slow, a layer thinner than a human hair each millennium. But over deep time, it adds up. And it means that beneath the surface, there might be other structures, other features equally well preserved, waiting for the next rover or the next radar sweep to reveal them. Some researchers wonder if Zhurong just got lucky. Did the rover happen to land in the one spot where a beach survived, or are there more 16 polygonal wedges scattered along its 1.2-kilometer route? Suggests that subsurface structures are common in this region, not rare. If freeze-thaw cycles and buried sediment layers are widespread across Utopia, Planitia, then the basin might contain an entire archive of coastal features, a distributed record of how the ocean behaved over millions of years. It seems as though Mars didn't have one beach. It had many. Miles of coastline shifting and evolving, shaped by water that rose and fell with climate changes we're only beginning to understand. And buried now, all of it under rust and silence. But not erased, not forgotten. Just waiting for someone to ask the right questions, to send the right tools, to listen carefully to what the ground has been trying to say. That's the gift Zhurong gave us, not proof of life. Not even definitive proof of an ocean, though the evidence leans heavily that way. What it gave us was specificity, a location, a depth, a set of features clear enough to study, analyze, and eventually visit again. The beach is still there. It hasn't gone anywhere in 3.5 billion years. It's not going anywhere now. And if there was one beach, there was a body of water large enough to create it. Something vast. Something that held enough liquid to carve shorelines, deposit sediment, and shape an entire hemisphere. We're drifting now toward that vastness, toward the idea of an ocean so large it covered nearly half a planet. A sea that didn't just exist, it endured. And the memory of it is still written in the land if you know where to look. Close your eyes for a moment and picture an ocean, not a lake, not a sea tucked between continents. An ocean so vast it stretches across an entire hemisphere, covering nearly a third of a planet's surface. Deep enough in places to swallow mountains. Wide enough that standing on one shore, you'd never see the other. Now, imagine that ocean on Mars, not as it is today, dry and frozen and silent, but as it might have been 4 billion years ago, when the sky was thicker and the sun's light fell differently on waves that actually moved. Scientists call it Oceanus Borealis, the Northern Ocean. And the evidence for it has been quietly accumulating for decades, each piece adding weight to a hypothesis that once seemed impossible. But Zhurong's discovery changed something. It gave us coordinates, a place where the ocean's edge might have rested where water met land, and left a signature we can still read. In 1987, a researcher named John Brandenburg proposed something radical. He looked at images from the Viking orbiters and noticed patterns in the northern plains of Mars, features that reminded him of shorelines on Earth. He called his hypothesis the Paleo-Ocean, an ancient body of water that once filled the basin we now know as Vastitas Borealis, the northern waste. At the time, most scientists were skeptical. Mars was too cold, they said, too dry. Any water would freeze solid or evaporate almost immediately. But Brandenburg persisted, and others began looking closer. Two features stood out in the orbital data. The first was a line called the Arabia Shoreline, running along the boundary between the northern lowlands and the southern highlands, at an elevation of roughly minus 3,800 meters. The second was the Deuteronilus contact, slightly lower around minus 4,200 meters. Both stretched for thousands of kilometers, curving around the planet's northern hemisphere like faint scars. They weren't perfectly level. Some sections rose higher, others dipped lower, but the overall pattern was unmistakable. Something had marked these boundaries, something fluid. Research shows that these proposed shorelines follow the edges of Vastitas Borealis, a basin so large it could hold all of Earth's continents with room to spare. The basin itself is an ancient impact feature, though exactly what created it remains unclear. Some believe it formed from a single massive collision early in Mars's history. Others suggest multiple impacts over time. Either way, the result was a depression roughly 4 to 5 kilometers below the planet's mean elevation, a natural reservoir where water, if it existed, would naturally collect. Scientists suggest that if this basin once held an ocean, the volume would have been staggering. Estimates vary, but most calculations point to somewhere between 30 and 60 million cubic kilometers of water. For comparison, Earth's Arctic Ocean contains about 18 million cubic kilometers. Mars's ocean would have been larger, not by a little, by a lot. And it would have covered roughly 19% of the planet's surface. Earth's Atlantic Ocean, by comparison, covers 17%. So, picture the Atlantic but on a smaller world, and you start to get a sense of scale. But here's what makes the hypothesis harder to accept. Those shorelines aren't level. When Michael Mallon and Kenneth Edgett analyzed them in 1998 using higher resolution cameras aboard the Mars Global Surveyor, they found that the Arabia feature varied in elevation by several kilometers. In some places, it was 3,000 meters below the mean. In others, it rose to 2,000 meters. That doesn't make sense for a stationary body of water. Water finds its level. It doesn't climb hills or dip into valleys unless something external forces it to. For years, that inconsistency was the strongest argument against the ocean hypothesis. If these weren't shorelines, what were they? Volcanic flows, ancient lava channels, erosion from wind over billions of years. Each alternative had problems of its own, but the uneven elevations seemed to rule out water. Until 2007, when two researchers, Taylor Perrin and Michael Manga, proposed a solution that changed everything. They suggested the shorelines were level when they formed. Mars itself had moved since then. The idea hinges on something called true polar wander, a process where a planet's entire outer shell shifts relative to its spin axis. It happens when mass redistributes unevenly across the surface, volcanic eruptions, pile material in one region, ice caps grow in another, large impacts carve out basins. Over millions of years, the planet's rotation adjusts to accommodate the new distribution and the axis shifts. When that happens, features that were once aligned with the equator or a particular latitude end up tilted, rising and falling across what appears to be uneven terrain. Perrin and Manga recalculated the elevations of the Arabia and Deuteronilus shorelines, adjusting for the estimated polar wander Mars experienced over the past 3 billion years. When they did, the lines leveled out. Not perfectly, but close enough to fit the profile of an ancient sea. The variations that had once seemed damning now made sense. The ocean had been real. The planet had just moved underneath it. In 1999, the Mars Orbiter Laser Altimeter, or MOLA, gave scientists the most precise topographic map of Mars ever created. Every hill, every valley, every crater measured to within a few meters of accuracy. And when researchers overlaid the hypothetical ocean boundaries onto that map, something became clear. The watershed for an ancient Martian ocean would have covered 3/4 of the planet's surface. That means rivers from nearly every region of Mars could have drained into the northern basin. Imagine snowmelt from the southern ice caps flowing downhill, carving valleys, picking up sediment, and carrying it all the way to the sea. A planetary-scale hydrological cycle. The Utopia Basin where Zhurong landed sits squarely within this hypothetical ocean. At 3,300 kilometers across, it's the largest impact crater in the solar system, dwarfing even Hellas Basin, which itself is over 2,000 kilometers wide. If Oceanus Borealis existed, Utopia would have been its deepest point, a submerged plain where the water might have reached depths of 1 to 2 kilometers. Not shallow, not a puddle, an ocean floor. Some believe the ocean's formation happened relatively quickly geologically speaking. During the late heavy bombardment, a chaotic period roughly 4.1 to 3.8 billion years ago, when asteroids and comets rained down on the inner solar system, Mars would have been hit repeatedly. Some of those impacts likely delivered water comets are mostly ice after all. Combine that with volcanic outgassing, where magma releases trapped water vapor into the atmosphere, and you have the raw material for an ocean. Add a thicker atmosphere to keep temperatures warm enough, and liquid water becomes not just possible, but inevitable. But how long did it last? That's the harder question. Some models suggest the ocean was stable for hundreds of millions of years, maybe even a billion. Others propose it was more transient forming during warmer periods and then freezing or evaporating when the climate cooled. The evidence doesn't give us a single clear answer. What it gives us is a range, a window of time when Mars had enough water, enough warmth, and enough atmospheric pressure to support an ocean that didn't just freeze solid the moment it appeared. Dr. Frederick Schmidt from the University of Paris-Saclay ran climate simulations in 2022 that painted a picture of what Mars might have looked like 3 billion years ago. His models suggested that much of the northern hemisphere could have had a climate similar to present-day Earth, not tropical, but temperate with stable liquid water at the surface. The ocean wouldn't have been warm, but it wouldn't have been entirely frozen either. Think of it like the North Atlantic. Cold, yes, but active, currents flowing, ice forming at the edges during winter, melting back during summer. A dynamic system. Research shows that the presence of an ocean would have dramatically affected Mars's climate in ways we're only beginning to understand. Water moderates temperature. It stores heat during the day and releases it at night. It evaporates, forms, clouds falls as rain or snow, and cycles back into rivers and seas. An ocean on Mars would have created weather systems, wind patterns driven by temperature differences between the water and land. Storms forming over the basin, sweeping across the highlands. Rainfall feeding rivers that in turn fed the ocean. A feedback loop. And here's something most people don't realize: water changes a planet's reflectivity. Ice and snow are bright reflecting sunlight back into space. Liquid water is dark, absorbing more heat. An ocean covering a third of Mars would have absorbed significantly more solar energy than the frozen desert we see today. That absorbed heat would have warmed the atmosphere, helping to sustain the liquid water in the first place. It's a delicate balance, and scientists suggest Mars might have teetered on the edge of it for a very long time. But oceans don't just sit still, they move. On Earth, tides are driven by the moon's gravity, which pulls on the water, causing it to rise and fall twice a day. Mars has 2 moons, Phobos and Deimos, but they're tiny, barely large enough to create noticeable tides. Phobos, the larger of the two, is only about 22 kilometers across. For comparison, Earth's moon is 474 kilometers in diameter, so Martian tides, if they existed, would have been weak, gentle, more like subtle swells than the dramatic surges we experience on Earth. Yet even weak tides matter. On Earth, tidal zones are some of the most biologically productive environments on the planet. The regular rise and fall of water concentrates nutrients, exposes fresh surfaces to sunlight, and creates pockets where chemistry happens faster. If Mars had tides, even small ones, the shorelines of Oceanus Borealis would have been zones of constant change. Water washing in, water retreating, sediment shifting, minerals mixing, energy flowing. Scientists also think the ocean might have experienced something more dramatic: tsunamis. In 2016, researchers analyzing images of the northern plains identified boulder fields and deposit zones that looked eerily similar to tsunami backwash on Earth. The evidence suggested 2 massive waves, each triggered by asteroid impacts into the ocean. The first tsunami, they estimated, carried boulders the size of cars or small houses, depositing them kilometers inland before the water retreated. The second happened when the ocean level had dropped by about 300 meters, and this wave carried a significant amount of ice which was left behind in valleys as the water drained. Calculations showed that these waves would have averaged 50 meters in height, though some could have reached 120 meters. That's taller than a 10-story building. The researchers determined that in Utopia, planitia specifically impact craters capable of generating such tsunamis would form roughly every 30 million years. That might sound rare, but over the span of hundreds of millions of years, it adds up. Multiple tsunamis reshaping the coast, erasing some features, creating others. And one more piece of evidence that the ocean wasn't static. It was alive with events. It seems as though Mars for a time was a water world. Not entirely not like early Earth, but enough. Enough to have shores and currents and storms. Enough to have zones where water met rock and sky and chemistry could unfold. Enough perhaps to support something fragile and microbial and brief. But we're getting ahead of ourselves. Before we can talk about what might have lived in that ocean, we need to understand how it could have existed at all. And that means understanding the sky above it, the atmosphere that held it together, the climate that kept it from freezing solid. Because Mars today is nothing like Mars back then. Something changed, something broke, and understanding what that was might be the key to understanding everything else. Think about the last time you felt rain on your skin, the way the air changes just before a storm, the smell of wet earth, the sound of thunder rolling across the sky. Weather isn't just something that happens, it's the pulse of a living planet, the breath between ground and space. And Mars, for a time, had that breath. Not the thin whisper we hear today, but something fuller, something that carried clouds and rain and snow across a world that wasn't yet a desert. Scientists studying ancient Mars have reconstructed what the climate might have been like during the Noachian period, roughly 4.1 to 3.7 billion years ago. The atmosphere was thicker then, much thicker. Estimates suggest atmospheric pressure at the surface could have reached 1,000 millibars, similar to what we experience on Earth today at sea level. Compare that to modern Mars, where surface pressure averages just 6 millibars, less than 1% of Earth's current atmosphere. That difference isn't subtle. It's the difference between water boiling away instantly and water pooling in valleys, flowing in rivers, collecting in seas. Research shows that Mars's early atmosphere was dominated by carbon dioxide just like today, but the sheer volume made all the difference. Carbon dioxide is a greenhouse gas. It traps heat. A thick CO2 atmosphere would have insulated the planet, preventing warmth from radiating back into space. The sun was dimmer 4 billion years ago, about 25 to 30% less luminous than it is now, which means Mars needed that extra insulation. Without it, the entire surface would have been frozen solid, locked in a permanent ice age. With it, temperatures could have risen above freezing at least in some regions, at least part of the time. But CO2 alone might not have been enough. Some models suggest that Mars's atmosphere also contained a small but crucial amount of hydrogen gas, perhaps 5 to 10% of the total. Hydrogen is an even more effective greenhouse gas than CO2. It absorbs infrared radiation across a broader spectrum, trapping heat more efficiently. Where might that hydrogen have come from? Scientists suggest several sources. Volcanoes releasing gases from deep within the crust. Chemical reactions between water and iron-rich rocks, a process that produces hydrogen as a byproduct. Even asteroid impacts, which can shock minerals in ways that free trapped gases. Whatever the source, that hydrogen could have warmed the planet just enough to keep water liquid at the surface. Picture Mars under that thicker sky. The atmosphere wouldn't have been transparent like Earth's. Carbon dioxide scatters light differently, giving the sky a faint orange or reddish hue even during the day. Clouds would have formed, but not the familiar white puffs we see from Earth. Martian clouds made mostly of water ice, with perhaps some CO2 ice mixed in, would have been thinner, more translucent, catching the sunlight in ways that created halos and strange optical effects. And at night, The clouds would have held the day's warmth close to the surface, slowing the planet's cooling, giving water more time to stay unfrozen. Rainfall on Mars would have been different too. The lower gravity, about 38% of Earth's, means raindrops would have fallen more slowly, drifting down like mist. Each droplet would have been smaller, less energetic when it hit the ground. Rivers carved by Martian rain wouldn't have been violent torrents, but slower, gentler flows, taking longer to erode valleys, but eventually creating the same kinds of features we see on Earth. Valley networks across the southern highlands of Mars suggest exactly this kind of erosion, branching channels that start small and grow wider as they descend, collecting tributaries carrying sediment toward the lowlands and ultimately toward the ocean. Some believe Mars experienced seasonal cycles, but not in the way Earth does. Our seasons are driven by axial tilt. Earth leans 23.5 degrees relative to its orbit. So as we circle the sun, different hemispheres receive more or less direct sunlight. Mars tilts about 25 degrees today, similar to Earth. But its obliquity, the technical term for axial tilt, isn't stable. Over millions of years, it wobbles dramatically, swinging anywhere from 15 degrees to 45 degrees or more. When the tilt is high, the poles receive much more sunlight during summer, causing ice caps to melt rapidly and dump water vapor into the atmosphere. When the tilt is low, the poles stay cold, year-round, locking water away as ice. Dr. Frederick Schmidt's climate models explored this variability. He found that during periods of high obliquity, Mars could have supported a northern ocean even with a relatively thin atmosphere. The extra sunlight at the poles would melt ice, releasing water vapor that increased atmospheric pressure and greenhouse warming. Clouds would form over the ocean, reflecting some sunlight, but also trapping heat below. Rainfall over the highlands would feed rivers that flowed back into the sea. It's a self-reinforcing cycle. Water begets warmth. Warmth begets more water. But it's also fragile. If something disrupts the cycle, it collapses quickly. And something did disrupt it. Around 3.7 billion years ago, Mars began losing its atmosphere. Not all at once. Not in a single catastrophic event. Slowly, molecule by molecule. Stripped away by the solar wind, a stream of charged particles constantly flowing outward from the sun. Earth's magnetic field deflects most of the solar wind, protecting our atmosphere. Mars once had a magnetic field too, generated by a liquid iron core churning deep below the surface. But the core cooled. The dynamo shut down. And without that protective shield, the solar wind began peeling away the atmosphere like wind eroding sand. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, measured this process in real time. Instruments aboard MAVEN detected ions, charged atoms, and molecules being accelerated away from Mars by interactions with the solar wind. The rate of loss is small, roughly 100 grams per second. That doesn't sound like much. 100 grams is about the weight of a bar of soap. But multiply that by billions of years, and you lose an ocean's worth of atmosphere. Mars didn't die quickly. It exhaled slowly into space. As the atmosphere thinned, the greenhouse effect weakened. Temperatures dropped. Water that once flowed freely began freezing. Some of it sublimated directly from ice to vapor, skipping the liquid phase entirely, and that vapor was also lost to space. Other water soaked into the ground, percolating down through cracks and pores in the rock, eventually freezing in the subsurface as permafrost. NASA's InSight lander, which operated from 2018 to 2022, detected seismic waves that suggest vast reservoirs of ice buried kilometers below the surface. Enough water scientists estimate to cover the entire planet in an ocean 1 to 2 kilometers deep. It's still there, just locked away out of reach. But before the atmosphere thinned completely, there would have been a transition period, a time when Mars wasn't fully warm and wet anymore, but wasn't yet the frozen desert we see today. Research shows this intermediate phase, called the Hesperian period, lasted from about 3.7 to 3 billion years ago. During this time, water still existed on the surface, but only intermittently. Perhaps the ocean froze over completely, turning into a massive ice sheet. Perhaps it melted seasonally, with cracks and leads opening up during warmer months, allowing liquid water to briefly touch the air before refreezing. Some believe volcanic activity played a crucial role during this transition. Mars has some of the largest volcanoes in the solar system: Olympus Mons, Arzia Mons, Pavonis Mons. These shield volcanoes formed over millions of years, erupting slowly and steadily, pouring lava across the plains and releasing gases into the atmosphere. Each eruption would have temporarily thickened the atmosphere, injecting CO2 and water vapor, and perhaps other gases that warmed the planet just enough to melt surface ice. But between eruptions, the atmosphere would thin again, and the water would refreeze. A cycle of freezing and thawing over and over, leaving behind the polygonal wedges and layered deposits that Jurong detected in Utopia Planitia. Think about what that means for a moment. The freeze-thaw cycle suggests that water didn't just disappear overnight. It lingered. It came and went. It carved features into the landscape during brief periods of warmth, and then retreated underground or into the ice caps when the cold returned. This punctuated habitability, as some scientists call it, creates a very different picture than a planet that was either always wet or always dry. Mars oscillated. It flickered between habitable and inhospitable, and the length of those habitable windows, days, months, years, centuries, determined whether anything living could have taken hold. Dr. Edwin Kite from the University of Chicago has studied Mars's climate history extensively. He described the planet as capable of self-regulation, but only to a point. Earth regulates its temperature through a carbon cycle that involves plate tectonics weathering and volcanic outgassing. Mars had something similar, but less stable. During warm periods, CO2 would react with water and rocks, forming carbonates that locked the gas away in solid form. That would cool the planet. Then volcanic eruptions would release more CO2, warming it again. But without plate tectonics to recycle the carbonates back into the mantle, the cycle eventually broke down. Mars ran out of easily accessible CO2. The atmosphere thinned beyond recovery, and the water froze for good. Scientists analyzing data from the Curiosity rover, which has been exploring Gale Crater since 2012, found evidence of this transition preserved in the rock layers. Lower down older rocks show signs of flowing water, rounded pebbles, cross-bedded sandstones, mudstones that formed in ancient lake beds. Higher up, younger rocks are drier, more cracked, showing exposure to wind and cold, but little liquid water. It's like reading a diary of climate change written in stone. Each layer tells a story of what the sky was like when that layer formed. And the story moves from wet to dry, warm to cold, alive with possibility to frozen in silence. Yet, even in the cold water, found ways to persist. Perchlorate salts discovered in Martian soil by the Phoenix lander in 2008 lowered the freezing point of water significantly. A brine solution, water mixed with salts, can stay liquid at temperatures as low as -70 degrees Celsius. That's colder than any natural environment on Earth's surface, but on Mars it's common. During summer afternoons, when sunlight warms, the ground brines might form in the top few centimeters of soil, seeping through dust and sand before refreezing at night. Jurong detected minerals consistent with these brines, hydrated salts like sulfates and perchlorates, suggesting that even today, under the right conditions, liquid water occasionally appears on Mars for brief moments. But here's the paradox. Mars needed warmth to sustain an ocean, but warmth requires an atmosphere, and an atmosphere requires volcanic activity or some other continuous source of gas to replace what the solar wind strips away. Once the volcanoes quieted, the cycle collapsed. The ocean didn't evaporate all at once. It froze. It sublimated. It soaked into the ground. Over hundreds of millions of years, the water that once covered a third of the planet's surface disappeared from view, leaving only traces minerals in the soil ice beneath the surface valleys, carved by rivers that no longer flow. It seems as though Mars was never meant to be a water world permanently. It was too small, its core cooling too quickly, its magnetic field fading too soon. Earth, by comparison, is still geologically active, still recycling gases, still maintaining the balance that keeps liquid water on the surface. Mars lost that balance. But for a while, maybe a few 100 million years, maybe longer, it had weather. Real clouds and rain and snow, storms sweeping across the ocean, ice forming at the edges during winter, melting back during summer. A sky that held the warmth just long enough. And if water persisted that long, if the climate stayed stable enough for valleys to form, and sediment to settle, and beaches to accumulate grain by grain, then something else becomes possible. Not guaranteed, not inevitable, but possible. Because everywhere on Earth, where liquid water touches rock and air, where energy flows and chemistry unfolds, something stirs. Life finds a way. And we're left wondering, did Mars have just enough time? Sometimes the past doesn't vanish. It hides, seeps into cracks, crystallizes in stone, waits in the dark for someone to notice. And on Mars, water left more than memories. It left fingerprints, chemical signatures locked inside minerals that Zhurong could read even billions of years later. Not flowing rivers, not crashing waves, but something quieter. Water that stayed behind when the ocean disappeared, trapped in the ground, frozen in time, speaking through the rocks about what once was. When scientists analyzed the data from Zhurong's instruments, the spectrometers, the cameras, the radar, they found something unexpected in the bright-toned rocks scattered across Utopia Planitia. These rocks weren't like the darker basalts common on Mars, the volcanic stone that covers much of the surface. They were lighter in color, almost pale, and their spectral signatures revealed the presence of hydrated minerals. Minerals that form only in the presence of water. Not ancient water from billions of years ago, necessarily, but water that persisted much later than anyone thought possible, well into what's called the Amazonian period, the dry frozen era that began about 3 billion years ago and continues today. Research shows that among these hydrated minerals were sulfates, compounds like gypsum and kieserite, along with hydrated silica, particularly a form called opal CT. On Earth, these minerals typically form when groundwater dissolves ions from surrounding rock and then evaporates, leaving behind crystals. The same process can happen when subsurface ice melts temporarily, perhaps from volcanic heat or seasonal warming, and the meltwater percolates upward through soil before evaporating at the surface. What remains is a hard, crusty layer that geologists call Duri crust. Duri crust isn't unique to Mars. You can find it in Earth's deserts, places like the Atacama in Chile or the Australian outback, where water tables fluctuate and minerals precipitate near the surface. The crust that forms is tough, resistant to erosion, sometimes several centimeters thick. On Mars, Zhurong detected a similar layer in the rocks it examined, suggesting that liquid water, even if only in small amounts, had been moving through the soil at this location relatively recently. Not yesterday, not 1,000 years ago, but perhaps within the last few 100 million years, which in geological terms is almost modern. Scientists suggest that the water responsible for these minerals came from one of two sources, possibly both. The first is rising groundwater. Deep below the Martian surface, there are likely aquifers, layers of porous rock saturated with ice. If heat from volcanic activity or from radioactive decay in the crust warms these layers, the ice melts and liquid water begins migrating upward through fractures and pores drawn by capillary action and pressure gradients. When it reaches the surface, the low atmospheric pressure causes it to evaporate quickly, but the dissolved minerals stay behind, cementing soil particles together into that hard, Duri crust. The second possible source is melting subsurface ice caused by changes in Mars's obliquity. When the axial tilt increases during its long cycles, more sunlight reaches the poles and mid-latitudes, warming the ground, enough to melt ice buried just below the surface. That meltwater doesn't necessarily pool on the surface. It might seep laterally through soil layers, reacting with minerals, depositing salts, and then refreezing when temperatures drop again. Over millions of years, repeated cycles of melting and refreezing would create the kind of mineral-rich crust Zhurong found. But there's more in the rocks than just sulfates and silica. The spectrometers also detected ferrihydrite, a form of iron oxide and possibly chloride salts like those found in seawater on Earth. Ferrihydrite is particularly interesting because it's an intermediate mineral, a transitional phase that forms when iron-rich water reacts with oxygen. Over time, ferrihydrite usually converts into more stable forms, like hematite, the red iron oxide that gives Mars its color. The presence of ferrihydrite suggests that the water chemistry was active relatively recently, geologically speaking, because if it were ancient, the mineral would have already transformed into something else. Some believe the chlorides point to something even more intriguing: briny water. Salt water has a much lower freezing point than pure water. Depending on the concentration and type of salt, brines can remain liquid at temperatures as low as -70 degrees Celsius. That's far colder than any ocean on Earth, but on Mars, it's within the range of what occurs seasonally in certain regions. During summer afternoons, when sunlight warms the surface, thin films of brine might form in the top few centimeters of soil, wetting the dust before evaporating or refreezing at night. Zhurong's discovery of chloride-bearing minerals supports this possibility. Dr. Xiaoguang Qin from the Chinese Academy of Sciences led a study analyzing dune formations near Zhurong's landing site. His team found surface features that looked like cracks, ridges, and aggregated sand particle structures, consistent with repeated wetting and drying cycles. The patterns reminded them of polygonal cracks seen in terrestrial mud flats where water evaporates, the soil contracts, and fractures form in geometric shapes. On Mars, these cracks appeared to be cemented by hydrated minerals, suggesting that moisture had been present long enough to dissolve. Ions move them through the soil and precipitate them as the water disappeared. The age of these dunes, estimated at between 400,000 and 1.4 million years old, suggests that the water activity happened relatively recently in Mars's history, not during the warm, wet Noachian period billions of years ago, but during the cold, dry Amazonian epoch. That's surprising. Most scientists assumed that by the Amazonian Mars was too cold, and its atmosphere too thin to support liquid water, anywhere even briefly. But the evidence from Zhurong suggests otherwise. Water found a way to persist, hidden in the soil, emerging during rare moments of warmth, leaving traces that we can still detect today. Think about what that means. Mars isn't just a dead planet with a distant past. It's a planet where water even now might still be cycling through the ground in slow, invisible rhythms. Not rivers, not oceans, but something. Moisture creeping through fractures, ice melting and refreezing, chemistry happening in the dark out of sight, waiting for the next warm season, or the next volcanic pulse to bring it briefly to the surface again. It's not habitability in the way we usually think of it, but it's not complete sterility either. It's something in between, a flicker of activity in a mostly frozen world. Beneath the surface, conditions are even more promising. NASA's InSight lander, which operated from 2018 until late 2022, used a seismometer to listen to Marsquake's tremors caused by the planet's cooling crust, cracking and shifting. By analyzing how seismic waves traveled through the interior, scientists were able to map the structure of Mars's crust and upper mantle. What they found was striking. The crust is full of cracks and pores, spaces between rock grains where water could potentially reside. And seismic data suggested that much of this pore space, especially at depths between 10 and 20 kilometers, might be saturated with liquid, not pure water. At those depths, pressure and residual heat from the planet's interior keep temperatures just above freezing, but the water would be briny, mixed with salts that further lower its freezing point. Scientists estimate that if all this subsurface water were somehow extracted and spread evenly across Mars's surface, it would form a global ocean 1 to 2 kilometers deep. That's more water than currently exists in all of Earth's rivers, lakes, and underground aquifers combined. It's still there, just hidden, locked away in the Martian crust like groundwater in a desert accessible only if you dig deep enough. Research shows that this deep water might have been there since the ancient ocean disappeared. As the climate cooled and the surface froze, water didn't just evaporate into space. Much of it soaked into the ground, percolating downward through fractures until it reached depths where pressure and temperature balanced in a way that allowed it to remain liquid. Over billions of years, that water has probably been interacting chemically with the surrounding rock-dissolving minerals, precipitating others, perhaps even supporting microbial life in the deep subsurface if any life ever got started on Mars in the first place. Dr. Michael Manga, who co-authored the study on InSight seismic data, noted that even though this deep water isn't directly accessible for life as we know it, the fact that it exists means Mars once had and might still have the basic ingredient necessary for biology. Water, liquid water. Not everywhere, not all the time, but somewhere in the cracks and pores of a fractured crust, chemistry continues. Slowly, quietly, out of reach. Some believe that understanding where the water went is just as important as understanding where it came from. Mars likely had enough water 4 billion years ago to cover its entire surface in a layer about 137 meters deep, possibly more if you include ice locked in polar caps and subsurface deposits. That's roughly equivalent to Earth's Arctic Ocean. But today, the visible water on Mars ice in the polar caps frost, in shadowed craters, trace vapor in the atmosphere, accounts for only a fraction of what must have been there originally. The rest is either locked underground, as InSight data suggests, or lost to space stripped away by the solar wind over billions of years. Scientists studying isotopes in the Martian atmosphere have found evidence of this loss. Isotopes are variations of the same element with different numbers of neutrons. Hydrogen, for example, comes in 2 forms: regular hydrogen with 1 proton and no neutrons, and deuterium with 1 proton and 1 neutron. Deuterium is heavier, so when water molecules evaporate and escape into space, regular hydrogen escapes more easily than deuterium. Over time, the ratio of deuterium to hydrogen in the remaining water increases. Mars's atmosphere today has a much higher deuterium to hydrogen ratio than Earth, suggesting that a significant amount of water has been lost to space. By comparing the current ratio to the ratio preserved in ancient Martian meteorites, scientists calculated how much water Mars must have had originally. The numbers point to an ocean covering at least 19% of the planet's surface, possibly more. Where did it go? Some evaporated and was stripped away by solar wind. Some froze into polar caps. Some soaked into the crust and remains there still hidden but not gone. And some might have been chemically bound into minerals locked into the crystal structure of rocks in a process called hydration. Those hydrated minerals Jurong found, they're part of that story. Water that didn't flow away or evaporate. Water that stayed transformed, embedded itself in stone. It seems as though Mars didn't lose its water all at once in some catastrophic event. It lost it gradually, piece by piece, over billions of years. The ocean evaporated. The rivers dried up. The ice retreated underground. And what remained was a surface that looks dry, but holds secrets just beneath. Every bright-toned rock, every mineral-rich crust, every polygon carved by freeze-thaw cycles is a reminder that water was here, that it shaped this world, and that in some hidden corners it might still be shaping it now, one molecule at a time, in rhythms too slow for us to see, but written clearly in the chemistry of the soil. The minerals Jurong detected aren't just data points. They're evidence of a planet that refuses to be entirely dead. A planet where water, even after the ocean vanished, found ways to persist. Not as waves or rain or flowing rivers, but as moisture in the soil ice beneath the surface brines that briefly thaw during rare warm days. It's not the Mars we imagine blue and Earth-like, but it's not the barren, lifeless rock we once thought either. It's something in between. A world still holding on to its past, still carrying water in its bones, still whispering through the minerals about a time when things were different. And if water found ways to persist for billions of years, hiding in the cracks emerging when conditions allowed, then maybe it wasn't the only thing that found a way. Because life, at least on Earth, doesn't need much, just water, a source of energy and time. And Mars, despite everything, still has traces of all three. Here's a question that keeps scientists awake at night. If you had an ocean stable for millions of years, with shorelines where water met rock and sunlight filtered through the atmosphere, would that be enough? Enough for chemistry to become biology? Enough for molecules to organize into something we might recognize as alive? On Earth, the answer seems to be yes. Life appeared quickly almost as soon as conditions allowed. But Mars isn't Earth. It never was. And the search for life there is less about finding what thrived and more about finding what might have tried. When astrobiologists talk about habitability, they're measuring a specific set of conditions, not comfort, not abundance, just the bare minimum required for life as we understand it to exist. Liquid water is the first requirement. Life needs a solvent, a medium where molecules can dissolve, move, and interact. On Earth, that medium is water. Every organism we've ever studied, from bacteria in hydrothermal vents to humans, depends on liquid water at some stage of its existence. Mars had water. For how long? That's the critical question. Because the origin of life doesn't happen overnight. It requires time, hundreds of thousands, perhaps millions of years, for the right molecules to form, to find each other, to stumble into configurations that can replicate, metabolize, and evolve. Research shows that on Earth, life appeared remarkably fast. The planet formed about 4.5 billion years ago. The earliest evidence of life chemical signatures and rock formations from Greenland and Western Australia dates back to roughly 3.8 billion years ago. That's only 700 million years after Earth's formation. During much of that time, Earth was being bombarded by asteroids and comets, its surface repeatedly sterilized by impacts. Yet, as soon as the bombardment slowed enough for liquid water to persist, life appeared. Or at least life's traces appeared. The organisms themselves were probably much older, having evolved earlier, but leaving no fossils behind. Mars experienced the same bombardment, the same violence, the same eventual calming. And the Noachian period on Mars, when the ocean likely existed, overlaps almost perfectly with the time life was emerging on Earth. Two planets separated by tens of millions of miles, both with liquid water, both bathed in sunlight, both full of the raw chemical ingredients, carbon, nitrogen, phosphorus, sulfur, that biology requires. If life started on Earth during this window, why not Mars? Scientists suggest that the most likely place for Martian life to begin would have been in shallow coastal environments, shorelines, tidal zones, the places where ocean met land. On Earth, these environments are extraordinarily productive. Nutrients wash down from rivers concentrated by evaporation, mixed by waves. Sunlight penetrates to the bottom, providing energy for photosynthesis. Minerals from volcanic rock dissolve into the water, creating a chemical soup rich in elements life can use. And the constant cycling of water tides, rising and falling, waves washing sediment back and forth, creates microenvironments where chemistry happens faster, where molecules have more opportunities to interact. Dr. Benjamin Cardenas from Penn State, who has spent years studying Martian sedimentary deposits, often points out that on Earth, the earliest fossils we've found come from precisely these kinds of settings. Stromatolites, for example, layered structures built by colonies of cyanobacteria, are found in ancient tidal flats and shallow seas. The bacteria form mats on the sediment surface, trapping grains of sand and minerals. Over time, the mats grow upward layer by layer, creating rock formations that preserve the shape of the microbial communities. Stromatolites date back 3.5 billion years on Earth. They're evidence that life didn't just exist, it was already complex enough to build structures visible to the naked eye. Some believe Mars might have had something similar. If microbial life developed in the shallows of Oceanus Borealis, it would have left traces. Not necessarily fossil soft, microbial cells rarely fossilize, and even when they do, they're incredibly difficult to identify. But chemical traces, biosignatures, patterns in the rock that are hard to explain through geology alone. On Earth, certain minerals form preferentially in the presence of life. Iron bacteria, for example, concentrate iron oxide in specific ways. Sulfate-reducing bacteria alter the isotopic ratios of sulfur. Organic molecules, the carbon-based compounds that make up cells, can persist in rock for billions of years, detectable through spectroscopy. Zhurong wasn't equipped to search for biosignatures. Its instruments were designed for geology, not biology. But geology tells you where to look, where to. And what Zhurong found, those buried beach deposits, those hydrated minerals, that evidence of prolonged water activity points to exactly the kind of environment where life, if it existed, might have left clues. The southern edge of Utopia Planitia, where Zhurong roamed, was a transition zone. Not deep ocean, not dry highlands, the shallows, the shore. The place where conditions were most favorable. Research shows that life doesn't need much energy to survive, but it does need some. On Earth, the earliest organisms were probably chemotrophs, microbes, that got their energy not from sunlight, but from chemical reactions. Hydrogen reacting with carbon dioxide to produce methane, sulfur compounds being reduced to hydrogen sulfide, iron oxidation. These reactions release small amounts of energy enough for simple cells to maintain themselves, to grow, to divide. And they can happen anywhere water flows through rock-dissolving minerals and creating chemical gradients that life can exploit. Mars had those gradients: volcanic heat from below, cold water from above, minerals dissolving and precipitating. In the cracks and pores of the rock beneath Utopia, Planitia conditions might have been perfect for chemotrophic life. Not thriving, not abundant, but existing, quietly, out of sight, in the dark where energy flows and chemistry never stops. But here's where Mars's story diverges from Earth's. On Earth, once life got started, it spread rapidly. Ocean currents carried microbes across the globe. Rivers flushed them into lakes and seas. The entire planet became connected through water, and life colonized nearly every available habitat. Mars, even at its wettest, probably wasn't like that. The ocean was large, yes, but it was isolated in the northern basin. The southern highlands were drier, more fractured with water, locked in ice, or flowing intermittently through valleys that didn't always connect. Habitability on Mars was patchy, discontinuous. Life, if it started at all, might have been confined to small pockets, crater lakes, hydrothermal systems, aquifers deep underground, separated by vast stretches of inhospitable terrain. Dr. Francis Westall, an astrobiologist who studies early Earth and Mars, has written extensively about this concept of punctuated habitability. She argues that even if Mars had the right conditions for life to emerge, those conditions were never stable or widespread enough for life to evolve into complex multicellular forms. On Earth, life had billions of years of continuous habitability to experiment, to evolve, to fill every niche. Mars had at best a few 100 million years of intermittent habitability, and then the climate collapsed. The ocean froze. The atmosphere thinned. Whatever life existed would have had to retreat underground into the deep subsurface where liquid water persisted or go extinct. Some believe that if Martian life still exists, it's down there kilometers below the surface in aquifers, where pressure and geothermal heat keep water liquid. On Earth, we've found microbes living in similar conditions, deep in mines, in boreholes, drilled through kilometers of rock in aquifers isolated from the surface for millions of years. These organisms are slow, their metabolisms barely ticking over, but they're alive. They survive by extracting energy from the rock itself, using chemical reactions that don't require sunlight or organic matter from the surface. Mars might harbor the same kind of life, hidden, unreachable, but there. Think about what that means for the search. We can't dig that deep yet. Our rovers barely scratch the surface, drilling centimeters into rock, occasionally a meter or two. To reach the deep aquifers would require technology. We don't have drills that can penetrate kilometers, keep samples uncontaminated, and function in the harsh Martian environment. It's possible, but it's decades away. So instead we search where we can. We look for places where the deep subsurface has been exposed. Crater walls, eroded escarpments, lava tubes, hoping that ancient water brought biosignatures to the surface where we can detect them. Scientists analyzing Martian meteorites have already found intriguing hints. In 1996, a team led by David McKay announced that a meteorite called ALH 84001, which originated from Mars and landed in Antarctica, contained structures that resembled fossilized bacteria. The announcement was controversial. Most scientists argued that the structures could be explained by non-biological processes, and the claim was never widely accepted, but the debate it sparked was valuable. It forced researchers to define exactly what constitutes a biosignature, to develop better tools for distinguishing biology from geology, and to recognize how difficult it is to prove that something lived billions of years ago on another planet. Research shows that the most convincing biosignatures aren't single features but patterns. Multiple lines of evidence that taken together are hard to explain through geology alone. On Earth, when we find ancient microbial life, we find several things at once. Organic molecules with specific isotopic ratios, minerals arranged in ways that biology typically produces, microscopic structures that look like cells or cell walls, sedimentary textures consistent with microbial mats. No single piece is definitive, but the combination builds a case. Mars requires the same approach. We need to find multiple biosignatures in the same location, preserved in the same rock, pointing to the same conclusion. The beaches Jurong discovered are promising candidates for this kind of search. On Earth, beaches are excellent places to find fossils. Sediment accumulates, slowly burying organic material before it can fully decay. Minerals precipitate from the water, replacing soft tissue with stone in a process called permineralization. The result is a fossil that preserves not just the shape, but sometimes even the cellular structure of the original organism. If Martian microbes lived along the shores of Oceanus Borealis, their remains might be locked in the sandstone layers Jurong detected, waiting for a future rover with the right instruments to find them. Some believe the discovery also raises a more profound question. If conditions were right for life to begin on Mars, and if life appeared on Earth almost as soon as it could, then maybe the origin of life isn't as rare as we thought. Maybe it's common. Maybe anywhere you have liquid water energy and time chemistry inevitably crosses the threshold into biology. Or maybe not. Maybe Earth got lucky and Mars didn't. The only way to know is to keep looking, to send more rovers, to drill deeper, to bring samples back to Earth, where we can analyze them with instruments far more sensitive than anything we can send to Mars. NASA's Perseverance rover, which has been exploring Jezero crater since 2021, is collecting samples for exactly this purpose. Jezero was once a lake fed by rivers that carved deltas still visible from orbit. The sediments in those deltas might contain biosignatures preserved in fine-grained clay, where organic molecules survive longest. Perseverance is caching samples in sealed tubes, leaving them on the surface for a future mission to retrieve. If all goes according to plan, those samples will be back on Earth sometime in the 2030s. And when they are, scientists will subject them to every test imaginable, searching for the faintest hint that life once stirred in Martian water. It seems as though the search for life on Mars is really a search for ourselves, a way of asking whether Earth's story is unique or universal, whether the spark that ignited here could have ignited elsewhere, under skies a different color, on shores no human has walked, and whether even after the ocean disappeared and the climate collapsed, that spark might still flicker somewhere deep below, in the dark beyond our reach, but not beyond hope. The evidence Zhurong provided doesn't answer these questions, but it sharpens them. It tells us where to look, what kind of environment might have supported life, and how long that environment might have lasted. The beach is there, the minerals are there, the water in some form is still there. What remains is patience, and the willingness to keep asking even when the answers take billions of years to find. Machines don't dream, they don't hope. They follow instructions, execute commands, measure what they're told to measure. But sometimes a machine outlives its design so thoroughly that it feels almost intentional, as if the rover itself wanted just a little more time. Zhurong was built to last 90 sols, 90 Martian days, about 3 Earth months. It lasted nearly 4 times that. And in those extra days, those borrowed moments on a world not its own, it found things no one expected. Then quietly it stopped, not broken, just tired, covered in dust, sleeping under a sky it will never see clearly again. The story of Zhurong is in many ways the story of ambition meeting reality. China had never landed anything on Mars before. The first attempt, Yinghuo 1 in 2011, failed before it even left Earth orbit when the Russian rocket carrying it malfunctioned. A decade later, they tried again, but this time they didn't send just a rover. They sent an entire system, an orbiter, a lander, and a rover, all in one mission. It was bold, risky. Most space agencies develop Mars missions, incrementally testing each component separately before attempting something complex. China did it all at once, and somehow it worked. Tianwen-1 launched on July 23, 2020, during a narrow window when Earth and Mars were aligned favorably for interplanetary travel. The journey took 202 days, a slow arc through the void, the spacecraft following a precisely calculated trajectory that would deliver it to Mars with enough velocity to capture into orbit, but not so much that it would overshoot. On February 10, 2021, the spacecraft's engines fired, slowing it just enough to be caught by Mars's gravity. It became China's first successful Mars orbiter. For 3 months, it circled the planet, cameras surveying the surface radar, probing for subsurface ice mission, planners studying potential landing sites and refining their approach. Research shows that landing on Mars is notoriously difficult. The atmosphere is thick enough to cause friction and heat, but too thin to slow a spacecraft down effectively with parachutes alone. Engineers call it the 7 minutes of terror, the time between entering the atmosphere and touching down, during which everything happens automatically, because radio signals take too long to travel between Earth and Mars for real-time control. The lander has to deploy a heat shield, release parachutes, fire retro rockets, and settle gently onto the surface all on its own, all in the correct sequence, all without human intervention. On May 14, 2021, the lander separated from Tianwen-1's orbiter and began its descent. 9 minutes of heat deceleration and precision. The entry capsule hit the upper atmosphere at nearly 20,000 kilometers per hour, friction heating the heat shield to over 1,000 degrees Celsius. At an altitude of about 11 kilometers, the parachute deployed, slowing the descent further. Then the heat shield detached and fell away, exposing the lander and rover to the Martian air for the first time. At about 100 meters above the ground, retro rockets fired, bringing the lander to a hover before descending the final distance. Sensors measured the surface, adjusted the angle, and at 11:11 p.m. UTC, Zhurong and its lander touched down softly in Utopia Planitia. China became the third country after the Soviet Union and the United States to successfully land on Mars. and the second after the United States to deploy a rover that transmitted data back to Earth. Scientists suggest that the landing site was chosen carefully. Utopia Planitia is flat, reducing the risk of the lander tipping over or hitting a boulder. But it's also scientifically interesting. Viking 2 had landed there in 1976, giving scientists decades of context about the region. And the hypothetical ancient shoreline of Oceanus Borealis runs through this basin, making it an ideal place to search for evidence of water. The specific landing zone was near the southern edge of the basin, close to a series of low ridges and escarpments that orbital images suggested might be remnants of that ancient coast. Zhurong itself is small, about 240 kilograms, roughly the size and weight of a large motorcycle. It has 6 wheels, each independently controlled, allowing it to navigate obstacles and climb slopes up to 20 degrees. A flat solar panel stretches across the top like a wing, capturing sunlight and converting it to electricity. Mounted on a mast are navigation cameras for driving, multispectral cameras for analyzing rock and soil composition. Beneath the rover, a ground-penetrating radar sends pulses deep into the soil, mapping layers and structures invisible from the surface. And at the front, an instrument called the Mars Surface Composition Detector uses lasers to vaporize tiny bits of rock, analyzing the light emitted to determine what elements are present. Some believe the mission was designed with humility. 90 souls might not sound like much, just 3 months, but it's realistic. Mars is harsh. Dust storms can block sunlight-starving solar panels. Temperatures swing wildly, dropping to minus 100 degrees Celsius at night, stressing electronics and mechanical parts. Wheels can get stuck in sand, motors can seize, and there's no way to fix anything. Once a rover's on Mars, it's on its own. So mission planners set conservative goals. 90 souls to explore as much as possible, gather data, test instruments, and hopefully contribute something meaningful to humanity's understanding of Mars. But Zhurong kept going, 100 sols, 200, 300. The solar panels, despite accumulating dust, continued generating enough power. The wheels, despite the rough terrain, kept rolling. The instruments, despite temperature swings and radiation, kept working. The rover traveled slowly, cautiously, about 200 meters on a good day, often less. It stopped frequently to take images, analyze rocks, probe the ground with radar. By the time it completed its primary mission, it had covered just over 1 kilometer. And then it kept going. Another kilometer. And another. Tracing a path roughly perpendicular to those hypothetical ancient shorelines, heading south toward the escarpments, gathering data every step of the way. Research shows that the rover's route was carefully planned to maximize scientific return. Engineers wanted to cross different geological units, areas where the surface composition or texture changed, to see how the environment varied across the basin. Some areas were smoother, covered in fine dust. Others were rockier with exposed bedrock and scattered boulders. Some showed signs of wind erosion, grooves carved into softer material. Others had small impact craters, their rims still sharp, suggesting they were relatively young. Zhurong photographed everything, measured. Everything, sent the data back to Earth through the Tianwen-1 orbiter, which relayed it across the solar system. Then came winter. Not Earth's winter, but Mars's. Because of the planet's axial tilt and its elliptical orbit, seasons on Mars are more extreme than on Earth, and they last longer, about twice as long, because a Martian year is 687 Earth days. In the northern hemisphere, where Zhurong was exploring, winter means less sunlight, colder temperatures, and the possibility of dust storms that can engulf entire regions. By May 2022, as winter approached, engineers made a decision. They would put Zhurong into hibernation, powering down non-essential systems to conserve energy, waiting for spring, when sunlight would return and temperatures would rise. Scientists suggest that this is a standard procedure for solar-powered rovers on Mars. NASA's Spirit and Opportunity rovers both experienced Martian winters, sometimes barely surviving them. The key is to position the rover in a spot with good sun exposure, tilt the solar panels toward the sun if possible, and hope that dust accumulation doesn't block too much light. Zhurong's engineers calculated that by December 2022, conditions should improve enough for the rover to wake up, automatically recharge its batteries, and resume operations. They left it there dormant in the middle of the plain and waited. December came. Then January, February. Silence. The rover never responded. Mission controllers tried repeatedly to establish contact, sending wake-up signals through the orbiter, but Zhurong remained quiet. In April 2023, Zhang Rongqiao, the mission's chief designer, explained what likely happened. Dust. Too much of it accumulated on the solar panels over the winter months. Even a thin layer of dust can reduce power generation significantly, and without enough power, the rover can't heat. Its electronics can't charge its batteries, can't activate its radio to call home. It's caught in a loop. Too cold to wake up, but needing to wake up to generate the heat required to clear the dust or recharge. Some believe Zhurong might still be salvageable. If a strong enough wind sweeps across Utopia Planitia, it could blow the dust off the solar panels. It's happened before. NASA's Opportunity rover, which landed in 2004 with a 90-sol mission, lasted 15 years in part, because Martian winds occasionally cleaned its panels, giving it renewed energy. But wind on Mars is unpredictable. It might come, it might not. And even if the panels were cleaned, there's no guarantee that the rover's electronics survived the prolonged cold. Components designed to operate within certain temperature ranges can fail permanently if they get too cold for too long. Solder joints crack, circuits break, batteries degrade. Research shows that the last data Zhurong transmitted was in May 2022, just before entering hibernation. It had traveled 1921 meters, just under 1.2 miles over the course of 358 days. Not far by human standards. You could walk that distance in 20 minutes, but on Mars, every meter is hard-won. Every measurement is precious. And the data Zhurong collected during those 358 days changed what scientists thought they knew about Utopia Planitia, about ancient water, about the possibility that Mars once had shores where waves actually broke. Think about what the rover accomplished with such a short life. It detected buried beach deposits. It found hydrated minerals suggesting water persisted longer than expected. It mapped subsurface layers with radar. It photographed dunes and rocks and crater walls. It analyzed soil composition. It proved that China could land on Mars, operate a rover there, and contribute meaningfully to the global effort to understand the red planet. All in less than a year, all with a machine that weighed less than a motorcycle and moved slower than a walking human. Scientists analyzing Zhurong's data are still publishing papers, still finding details in the measurements, still piecing together what the rover saw. The ground-penetrating radar profiles in particular are rich with information. Each pulse reveals layers, textures, density changes in the soil. Some layers are thin, others thick, some are smooth, others irregular. Each one represents a different period in Mars's history. A different set of conditions, water flowing, ice melting dust, settling impacts ejecting debris. It's a timeline compressed and buried waiting to be read. Some believe that Zhurong's silence isn't failure, it's completion. The mission exceeded every expectation. It lasted 4 times longer than designed. It traveled farther than required. It gathered more data than anyone dared hope for. And now it rests a small metal monument on an ancient plain, a marker that says, humans were curious enough to send something there, to ask questions, to search for answers, even when the answers are buried under billions of years of dust. But the story doesn't end with Zhurong. China has announced plans to send a sample return mission to Mars, possibly as early as 2028. If successful, it would beat NASA's Mars sample return mission, bringing Martian rocks and soil back to Earth, where they can be analyzed with instruments far more sophisticated than anything we can send to another planet. And the target for that mission, possibly Utopia Planitia, the same region Zhurong explored, the same ancient basin where an ocean might have lapped against the shore, the same place where just maybe life once found a foothold. The rover sleeps, but its whispers still reach Earth. And in those whispers, carried across millions of miles of space, translated from radio signals into images and graphs and numbers, there's a story. A story about water and time and a planet that was once so different. A story that's not finished yet. Because what Zhurong found raises as many questions as it answers. And some of those questions can't be resolved by a single rover, no matter how determined. They require more missions, more data, more time. And that's what comes next, the search for what remains buried. The mysteries Zhurong could only hint at the answers, waiting beneath the dust for someone or something to uncover them. Science doesn't deal in certainties. It deals in evidence probabilities, the slow accumulation of data that either supports a hypothesis or quietly dismantles it. And when it comes to Mars, when it comes to the question of whether an ancient ocean truly existed, the evidence leans heavily in one direction. But leaning isn't proof, not yet. There are debate skeptics' alternative explanations. There are things we still don't know, questions Zhurong's data raised but couldn't answer. And beneath the surface of Utopia, Planitia, beneath the dust and rock and frozen ground, there are secrets waiting. Some we might uncover in the next decade. Some might stay buried for centuries. Dr. Benjamin Cardenas, the planetary scientist who has spent years analyzing Martian sedimentary features, is cautiously optimistic about Zhurong's findings. He's studied the radar profiles, the mineral data, the images of the terrain. And while he believes Mars likely had an ocean, at some point, he's also aware of how difficult it is to prove conclusively. The problem, he explains, is erosion. Mars has been geologically active for 4 billion years, not as active as Earth, but active enough. Wind has scoured the surface. Impacts have reshaped it. Volcanic flows have buried older features. The shorelines that might once have been crisp and obvious have been worn down, smoothed over, made ambiguous by time. Research shows that on Earth, coastal features erode relatively quickly. Wave action alone can reshape a shoreline in just a few thousand years. Add storms, tectonic shifts, and rising or falling sea levels, and most ancient coastlines disappear entirely or become so altered that identifying them requires careful analysis. Mars doesn't have tectonic plates, so the crust is more stable, but it does have other forces at work. Dust storms that can cover the entire planet, temperature swings that crack rocks, micrometeorites constantly pelting the surface. Over billions of years, even the most durable features fade. Some believe this is why the proposed shorelines of Oceanus Borealis are so hard to pin down. Orbital images show features that look like ancient beaches, terraces, ridges, parallel lines at consistent elevations. But when you examine them closely, they're not perfect. Some sections are clear, others are ambiguous. And in some places, the features disappear, entirely buried under lava flows from Elysium Mons, or smoothed away by eons of wind. It's like trying to reconstruct a shoreline on Earth after the ocean has been gone for 1 billion years. You'd find hints, traces, but definitive proof, that's harder. Dr. Bo Wu from Hong Kong Polytechnic University led the team that analyzed Zhurong's radar data and identified those buried beach deposits. He's confident in the findings, but acknowledges the limitations. Ground-penetrating radar can see structures beneath the surface, but it can't tell you exactly what those structures are made of. It can measure density layering, particle size. It can reveal shapes and angles, but it can't perform chemical analysis. It can't date the rocks. It can't definitively distinguish between sediment deposited by water and sediment deposited by wind or volcanic processes. That requires samples, physical samples brought back to Earth, where laboratories can subject them to every test imaginable. Scientists suggest that the strongest evidence for an ancient Martian ocean will come from isotopic analysis of rocks from the proposed shoreline regions. Isotopes are like fingerprints. Different processes, evaporation, freezing chemical weathering, alter the ratios of isotopes in predictable ways. If Mars had an ocean, the rocks along its shore should contain isotopic signatures consistent with prolonged exposure to liquid water. Oxygen isotopes in particular can reveal whether water was present and how it behaved. Did it evaporate slowly, leaving behind heavier isotopes? Did it freeze and sublime, which would produce a different pattern? The answers are in the rocks, but we need to bring those rocks home. That's where sample return missions come in. NASA's Mars Sample Return Program, a collaboration with the European Space Agency, aims to bring Martian rocks back to Earth sometime in the 2030s. The plan is ambitious. Perseverance rover, currently exploring Jezero Crater, is collecting samples and sealing them in tubes. A future mission will land near Perseverance, collect those tubes, launch them into Mars orbit rendezvous with an orbiter that will capture the samples and then return them to Earth. It's never been done before. The technical challenges are immense, but if successful, it will revolutionize our understanding of Mars. China, meanwhile, has announced its own sample return mission, tentatively scheduled for 2028 or 2030. If they succeed, they might beat NASA to the finish line, becoming the first nation to bring Martian soil back to Earth. And the target reports suggest it could be Utopia Planitia, the same region Zhurong explored, the same place where evidence of ancient water is strongest. Imagine what we could learn if we had physical samples from those buried beach deposits. We could date them precisely. We could analyze their mineral composition in detail. We could search for organic molecules, biosignatures, chemical traces of life. We could finally answer with confidence whether Mars had an ocean and how long it lasted. But samples won't solve every mystery. Even with rocks in hand, some questions remain stubbornly difficult. For instance, where did all the water go? We know some of it is locked in the polar ice caps, massive deposits of water, ice mixed with dry ice at both poles. We know some of it soaked into the crust and froze as subsurface permafrost. NASA's InSight data suggests there's enough water trapped underground to cover the planet in a global ocean 1 to 2 kilometers deep. But that still doesn't account for all of it. Estimates suggest Mars once had enough water to form an ocean covering 19% of its surface, possibly deeper than 500 meters in places. Where's the rest? Research shows that much of it was lost to space. The solar wind, a stream of charged particles from the sun, has been stripping Mars's atmosphere for billions of years, and water vapor in the atmosphere gets stripped away too. NASA's MAVEN spacecraft has been measuring this loss in real time since 2014, detecting ions accelerating away from Mars at a rate of about 100 grams per second. Over 4 billion years, that adds up to an ocean's worth of water. But it's a slow process. The ocean didn't vanish overnight. It froze, sublimated, and gradually leaked into space over hundreds of millions of years. Some believe there's also water chemically locked into minerals. When water reacts with certain types of rock, particularly olivine and pyroxene, common minerals in Martian basalt, it forms hydrated minerals like serpentine and clay. The water becomes part of the mineral's crystal structure, effectively trapped there until high temperatures or chemical reactions release it. Zhurong found evidence of these hydrated minerals. So did Curiosity, Spirit, Opportunity, and every other rover that's landed on Mars. The soil is full of them. If you could somehow extract all the water locked in Mars's crust and surface minerals, you might recover another significant fraction of the missing ocean. Scientists analyzing data from the European Space Agency's Mars Express orbiter have also detected what appear to be buried lakes of liquid water deep beneath the southern polar ice cap. The evidence comes from radar reflections consistent with liquid, though the interpretation is controversial. Some researchers argue the reflections could be from something else, saturated clay perhaps, or unusual rock formations. But if they are lakes, they'd be incredibly briny, full of salts that lower the freezing point enough to keep water liquid even at temperatures far below zero. Life in such an environment would be challenging, but not impossible. On Earth, we've found microbes living in similar extreme conditions. Yet, even with all this data with rovers and orbiters and decades of observation, some scientists remain unconvinced about the ocean hypothesis. They point to the uneven elevations of the proposed shorelines, the lack of undisputed coastal features, the difficulty of maintaining liquid water on the surface given Mars's thin atmosphere and cold temperatures. They suggest alternative explanations for the features Zhurong found: ancient volcanic flows, wind-eroded deposits, sediment laid down by catastrophic flooding events rather than a stable ocean. The debate isn't settled. Science rarely offers neat conclusions. It offers better and better approximations of the truth, each refined by new evidence. Dr. Edwin Kite from the University of Chicago has modeled Mars's climate extensively, trying to understand how long liquid water could have persisted on the surface. His models suggest that Mars might have experienced only brief periods of habitability, windows of time when the atmosphere was thick enough and temperatures warm enough for water to stay liquid. Between those windows, the planet would have been frozen, the water locked away as ice. It's a punctuated history, not steady habitability like Earth, but bursts of warmth interspersed with long, cold spells. If that's true, then the ocean Zhurong's data hints at might not have been permanent. It might have frozen and thawed multiple times, existing as liquid only during favorable climate swings. Think about how that changes the narrative. Instead of a stable ocean lasting hundreds of millions of years, we might be looking at an ocean that appeared froze, melted, and froze again over cycles spanning tens of millions of years each. Life, if it started during one of the warm phases, would have had to survive the freeze. On Earth, some microbes can do this. They form spores, enter dormancy, and wait for conditions to improve. Could Martian life, if it ever existed, have done the same? We don't know. But it's possible. Some believe the most exciting discoveries are still ahead of us. The Mars Ice Mapper mission proposed by NASA and international partners would use advanced radar to map subsurface ice across the planet in unprecedented detail. It could reveal hidden aquifers, buried glaciers, and regions where ice transitions to liquid water at depth. The European Space Agency's ExoMars Rosalind Franklin rover, currently delayed but still planned, will carry a drill capable of reaching 2 meters below the surface, deeper than any rover has gone before. That depth puts it below the zone where radiation has destroyed organic molecules, increasing the chances of finding biosignatures if they exist. Research shows that there's also growing interest in exploring lava tubes, natural tunnels formed by flowing lava that later drained away, leaving hollow passages beneath the surface. Mars has extensive volcanic regions, and orbital images have identified what appear to be collapsed sections of lava tubes, suggesting extensive underground networks. These tubes would be shielded from radiation, protected from temperature swings, and might even contain ice deposits. They are potential habitats for future human explorers. But they're also places where ancient life, if it retreated underground as the surface became uninhabitable, might still survive. Scientists are also beginning to think about Mars in terms of its deep biosphere. On Earth, we've discovered that life exists kilometers below the surface in aquifers and rock fractures far from sunlight. These organisms survive on chemical energy metabolizing minerals and gases released by geological processes. Mars might have a similar deep biosphere. If it does, finding it will require drilling far deeper than current rovers can manage, several kilometers perhaps. That's beyond our current capabilities, but it's not beyond imagination. Future missions, perhaps even crewed missions, could deploy drilling rigs designed to reach those depths. Yet all of this sample return, ice mapping, deep drilling, takes time, decades, perhaps longer. And even then, we might not find definitive proof of ancient life. We might not settle the ocean debate once and for all. Science doesn't always give us the answers we want. Sometimes it gives us more questions, better questions. Questions refined by data and observation. Questions that point toward the next discovery, the next mission, the next step in a journey that has no clear end. It seems as though Mars is teaching us patience, teaching us to live with uncertainty, teaching us that knowledge doesn't arrive all at once but accumulates slowly, layer by layer, like sediment settling on an ancient seabed. Every answer reveals new mysteries. Every discovery opens new possibilities. And beneath the rust and silence, beneath the dust that covers Jurong and the ice that hides ancient water, there are still things waiting. Things we'll find, things we'll wonder about, things that will keep us asking, keep us searching, keep us looking up at that small red dot in the night sky, and thinking, what else is there? There's a photograph taken by Jurong, not of rocks or craters or distant horizons, a selfie of sorts. The rover deployed a small wireless camera, set it on the ground a few meters away, and rolled into position. In the image, you can see the lander in the background, its ramps extended, and Jurong in the foreground, its solar panels catching the light, the Martian landscape stretching flat and rust-colored in every direction. It's a simple photo, almost mundane, but there's something haunting about it. A machine on another world looking at itself, documenting its own existence in a place where nothing should exist at all. That photograph reminds us of something we often forget. Mars isn't just data. It isn't just minerals and radar profiles and chemical signatures. It's a place. A real place with ground you could stand on, horizons you could walk towards, skies that change color as the sun sets. And for a brief moment in its 4 billion year history, something we built was there, moving across its surface, asking questions on our behalf. Jurong wasn't the first. It won't be the last. But it added something to the story. Something that matters. Scientists often talk about Mars as if it's a puzzle to be solved. A series of questions with answers hiding in the soil, waiting to be extracted through careful measurement and analysis. But maybe that's not quite right. Maybe Mars isn't a puzzle with a single solution. Maybe it's more like a conversation, a long, slow dialogue between us and a world that's been silent for eons, and we're only now learning how to listen. Every rover, every orbiter, every instrument we send is another way of asking, what were you? What happened here? And Mars answers quietly in layers of rock and traces of minerals and buried structures that take years to interpret. Research shows that we've been asking those questions for a surprisingly long time. The first successful Mars mission was Mariner 4, which flew past the planet in 1965 and sent back 22 grainy images. They showed craters, lots of craters. And for a while, scientists thought Mars was dead, geologically inactive, a barren moon-like world with nothing interesting to offer. Then came the Viking landers in 1976, which detected complex chemistry in the soil and raised the possibility, however slim, that something biological might be happening. The debate that followed lasted decades and still isn't fully resolved, but it changed how we thought about Mars. It made us wonder. Some believe the real turning point came in the early 2000s when rovers like Spirit and Opportunity found definitive evidence of ancient water. Not just traces, not ambiguous features. Actual sedimentary rocks formed in standing bodies of water. Hematite spherules, tiny round concretions nicknamed blueberries that form only in the presence of liquid. Mineral veins deposited by groundwater flowing through cracks. Cross-bedded sandstones shaped by currents. The evidence was overwhelming. Mars had been wet. And if it had been wet, maybe it had been habitable. Dr. Steve Squires, the principal investigator for the Spirit and Opportunity missions, once described the moment his team realized what they were looking at. Opportunity had driven into a small crater called Eagle and found layered rock exposed in the crater wall. The layers were thin, delicate, rippled in ways that only water can create. Squires said it was like opening a book that had been closed for billions of years. Every layer was a page, every mineral was a word, and the story they told was unmistakable. Water had been here, lots of it, for a long time. Zhurong's discovery adds another chapter to that story. A chapter about shorelines and beaches and an ocean so vast it covered a third of a planet. A chapter about water that didn't just flow through valleys or pool in craters, but spread across an entire hemisphere deep enough to support waves, stable enough to deposit sediment. Layer by layer over millions of years. It's not proof of life, but it's proof of the conditions life needs. And that's enough to keep us searching. Think about what we've learned in just the last few decades. We've gone from thinking Mars as a dead, cratered wasteland to understanding it as a world with a complex, dynamic history. A world that had rivers and lakes and possibly oceans. A world with weather seasons and climate cycles. A world that might still have liquid water hidden in its crust. A world where just maybe microbial life once existed and might still exist in deep underground refuges. All of that knowledge came from machines. Machines we built, launched, and guided across millions of miles of space. Machines that for a brief time became extensions of our curiosity. Scientists suggest that the next few decades will bring even more revelations. The samples Perseverance is collecting in Jezero Crater will eventually come back to Earth, and when they do, we'll be able to analyze them with instruments that don't fit on a rover. We'll measure isotopes with precision impossible on Mars. We'll search for organic molecules at the parts per billion level. We'll date the rocks to within a few million years. And if there are biosignatures, if there's any chemical or structural evidence of past life, we'll find it. Or we won't. But either answer tells us something important about how common or rare life is in the universe. China's planned sample return mission, if successful, will double the amount of Martian material available for study. 2 sets of samples from 2 different locations analyzed by 2 different scientific communities, compared and debated and re-examined. That's how science works best. Not in isolation, but in conversation. Not through a single mission, but through accumulated efforts over time. Every data point adds context. Every measurement refines the picture. And slowly the story becomes clearer. Some believe we'll eventually send humans to Mars. Not rovers, not orbiters, people. And when we do, they'll walk on the same ground. Zhurong crossed breathe air filtered through the same Martian dust and see the same rust-colored sky. They'll drill deeper, explore lava tubes, analyze rocks with tools far more sophisticated than anything a rover carries. They'll search for life in places robots can't reach. And maybe they'll find it, or evidence of it, or evidence that it almost happened but didn't. Any of those answers would be profound. But here's the thing. Even if we never find life on Mars, even if we search for 100 years and come up empty, the effort won't be wasted. Because the search itself teaches us. It teaches us how planets evolve, how atmospheres form and collapse, how water moves through a world over billions of years. It teaches us what conditions are necessary for life, and how fragile or robust those conditions might be. It teaches us in a very tangible way that Earth is rare, that the balance of factors that keeps our planet habitable, the magnetic field, the plate tectonics, the distance from the sun, the presence of a large moon, is not something to take for granted. Research shows that studying Mars helps us understand Earth's future. Our planet won't stay habitable forever. Eventually, billions of years from now, the sun will brighten and heat will make Earth's surface uninhabitable. But even before that, there are shorter-term concerns: climate change, atmospheric loss, the delicate balance that keeps liquid water on the surface. Mars is a cautionary tale. It's a planet that had water lost it and became a frozen desert. Understanding how and why that happened might help us protect what we have. It seems as though Mars holds a mirror up to Earth. Not a perfect mirror. The reflection is distorted by differences in size, distance from the sun, and geological history. But it's close enough to be instructive, close enough to make us think, close enough to remind us that worlds change, that habitability isn't permanent, that the conditions we depend on are maintained by processes we're only beginning to understand. There's a poem by Diane Ackerman that says, "We are Earth's awareness of itself." And maybe that's what Mars exploration is really about. Not just studying another planet, but becoming aware of our own. Using the distance, the millions of miles of space between here and there to gain perspective. To see Earth not as the unchanging stage on which human history unfolds, but as a dynamic, fragile system that's been lucky enough to stay habitable for billions of years. Mars wasn't so lucky, but it came close. And that closeness is what makes it so compelling. So where does that leave us with a rover asleep on a dusty plain, its solar panels covered, its instruments silent? With orbiters circling overhead, cameras watching for changes, radar probing for ice. With samples waiting to be retrieved. With questions that don't have answers yet, but might soon. With plans for future missions, rovers that drill deeper orbiters, that map more precisely landers, that search for life in places we haven't looked before, with the knowledge that every answer we find leads to new questions, and that's not frustration, that's progress. Zhurong found a beach buried under 10 meters of dust and rock, a beach that hasn't seen water in 3.5 billion years, a beach that tells us Mars was once different, wetter, possibly alive with chemistry complex enough to matter. The rover found minerals that speak of water persisting longer than expected, cycling through the soil during brief warm periods long after the ocean disappeared. It found polygons formed by freeze-thaw cycles, evidence that ice and liquid coexisted in rhythms we're only beginning to map. It found all of this in less than a year, covering barely more than a mile using instruments that fit on a machine the size of a motorcycle. What might we find if we keep looking? What's buried deeper, farther in places we haven't explored yet? What's locked in the polar ice, the subsurface aquifers, the ancient rocks of the southern highlands? What's waiting in the lava tubes, the crater floors, the regions where hydrothermal systems once circulated hot water through fractured crust? We don't know, but not knowing is part of the beauty. Not knowing is what keeps us searching. Here's a question for you. If you could ask Mars one question, just one, what would it be? Would you ask if it ever had life? Would you ask where the water went? Would you ask what it felt like when the atmosphere thinned and the oceans froze and the world went quiet? Or would you ask something simpler, something more personal? What was it like when you were warm, when you had rain and rivers, and maybe even something small and microbial swimming in your shallows? Maybe Mars can't answer. Maybe the only answers are the ones we find ourselves slowly, patiently through decades of exploration and analysis and debate. But that doesn't make the question less important. It makes it human. It makes it ours. The rover sleeps beneath a Martian sky that changes from pink to blue as the sun sets, then black as night falls, and stars emerge, stars we see from Earth too. But from a different angle, a different perspective. Somewhere in that darkness, Earth is visible as a pale blue dot, a tiny spark of light barely distinguishable from the background. Carl Sagan once called Earth that a pale blue dot and asked us to consider how fragile and precious it is. From Mars looking back, the sentiment is even sharper, because from there you can see what Earth has and Mars lost. Atmosphere, water, life, color, warmth. Zhurong is silent now, but its data isn't. The information it gathered is still being analyzed, still sparking papers and debates and new hypotheses. The beach it found is still there unchanged by time, because time on Mars moves slowly. The minerals are still there, recording chemical signatures that tell stories about water and warmth and moments when the planet wasn't quite as frozen as it is now. And that record will stay preserved in stone until someone or something returns to read it again. In the rust and silence, history holds its breath. It waits for the next rover, the next orbiter, the next human explorer to arrive and ask the next question. It waits with the patience only. Geology has the patience of dust. settling grain by grain of ice forming and melting and forming again, of planets orbiting through deep time, while their surfaces change and their stories accumulate in layers no eye has seen. We've drifted together through an ancient ocean that exists now only as memory and evidence. We've walked along shores that haven't felt waves in billions of years. We've listened to what a small rover whispered back across the void, messages about water and rock, and the possibility, however faint, that Mars once had what Earth has now. We don't know how the story ends. Maybe it doesn't end. Maybe it just keeps unfolding chapter by chapter, discovery by discovery, as long as we keep looking. Thank you for drifting with me through this quiet journey, for listening as Mars spoke through minerals and radar echoes and buried layers of sand, for wandering alongside scientists who dedicate their lives to understanding a world they'll never walk on, for being curious enough to spend time with a story that has no neat conclusion, only better and better questions. If this journey brought you some comfort, some wonder, some sense of connection to the vast and ancient universe we're part of, then perhaps you'll join me again. There are more stories out there, more worlds, more mysteries written in stone and ice and the light of distant stars, more whispers from the dark waiting to be heard. Sleep well, dream of distant shores, and when you look up at the night sky, remember Mars is there, small and red and patient, holding its secrets close, waiting for us to return and ask again, what were you? What happened? What remains? Good night